Hey everyone, Mr. Hauk here. In today's video, we're going to be simplifying using the double angle formulas. Alright, let's go and get started. So in many of the previous videos, we've been simplifying with the reciprocal identities, quotient identities, Pythagorean identities, and in the most recent video, I think we simplified using the sum and difference formulas. So now we're going to continue simplifying, but now with the addition of the double angle formulas that you see right here. So sine of 2 theta equals 2 sine theta cosine theta, cosine of 2 theta equals cosine squared theta minus sine squared theta, and tangent of 2 theta equals 2 tangent theta over 1 minus tangent squared. Now, one thing that's not here on this formula sheet is the fact that cosine of 2 theta actually has two other variants. Not only do we have cosine squared minus sine squared, but cosine of 2 theta can also be 2 cosine squared theta minus 1, or 1 minus 2 sine squared theta. And I'll actually be making use of these, or at least this one here in the middle, in this video. So let's go and see some examples. For these examples, again, like many of our problems that we've done before, our goal is to simplify down to a single trig expression or a constant, okay? So we're going to start here with example 1, sine squared x over sine of 2x. Now the first thing that I notice is the sine of 2x, that's a double angle, and the double angle formula for sine is sine of 2x is equal to 2 sine x cosine x. So I'm going to go ahead and make that replacement there. Now notice that our numerator, sine squared of x, well, remember that sine squared is really just, sine of x times itself. And one of these sine of x's will cancel with this sine of x in the denominator. So we'll have sine of x over 2 cosine x. And also, remember that sine of x over cosine x is tangent of x. So what we now have is tangent of x over 2. Or, 1/2 times sine x over cosine x. And then this is where I turn the sine of x over cosine x into tangent x. So we get 1/2 tangent x or tangent x over 2. Same thing. Okay? So again, in every one of these examples, you're going to see some application of a double angle formula. All right, here's example 2. We have tangent of 2x over 2 sine x cosine x. And at first glance, you see this tangent of 2x and you might think, okay, well, let's use the double angle formula for tangent. Make this, hopefully makes the problem a little easier. But there's actually something different that I see. I see this 2 sine x cosine x, and this is equal to sine of 2x. So instead of changing the tangent to x, I'm actually going to change the 2 sine x cosine x into sine of 2x. So now I have tangent of 2x divided by sine of 2x. Next, I'm going to take this tangent of 2x, I'm going to split it into sine of 2x over cosine of 2x. I'm just going to rewrite sine of 2x as sine of 2x over 1. And notice that we are now in a position where this can be where we can use keep, change, flip pretty successfully. So that's what I'm going to do next. Sine of 2x over cosine of 2x times, so with the keep, change, then flip this, so we have 1 over sine of 2x. And notice that the sine of 2x and the sine of 2x will cancel, leaving us with 1 over cosine of 2x. However, we know that 1 over cosine is secant, so this will be secant of 2x as our most simplified answer. Okay, so different ways we can do this. If I would have changed this tangent of 2x using the double angle formula, it probably would have worked. Probably would have been more work in the long run though, because if you look at your double angle formula for tangent, you'd be making the problem, in my opinion, significantly more difficult, or it might not have been that much more difficult. Try it out, see what happens if you want. But I figured, I saw this here, saw that sine of 2x would be pretty useful to use, because then we'll have both of these angles in terms of 2x, which allows us to work with the tangent and sine pretty easily. Okay, moving right along, here's example 3. Cosine of x divided by 1 plus cosine of 2x. Right off the bat, we can see this cosine of 2x. Now remember, cosine of 2x though has a few different versions of what you can use. I'm going to end up using 2 cosine squared minus 1. And the reason I actually end up doing this is because we have this 1 plus right here. And I can see that this positive 1, and when we change this cosine of 2x into 2 cosine squared of x minus 1, this minus 1 and this positive 1 will end up canceling each other out. It's just something that, as you do more and more of these examples, these are the kind of things that you start to notice. So this is the replacement that I made. I end up using this formula. So replace cosine of 2x with 2 cosine squared of x minus 1. We can see the positive 1 and the negative 1 will combine to make 0. They cancel each other out. So all we have left is cosine of x over 2 cosine squared of x. And again, remember, cosine squared is just cosine of x times itself. So one of these will cancel with this in the top, leaving a 1 up there, by the way. So now we have 1 over 2 cosine of x. And we know that 1 over cosine is secant. So remember that we still have this 2 on the bottom, though. So it's either going to be 1/2 secant of x, or you can write it as secant of x over 2. These are the same thing. Okay. So again, big thing here was changing this cosine of 2x, and I used the version, to me, that would make things simplify the most, with this minus 1 that cancels with this plus 1. Okay, that was the thought process going on in my mind. All right, example 4. 2 tangent x times cosine squared of x divided by cosine of 2x. So what I actually end up doing here, I'm pretty sure you can go ahead and change the cosine of 2x if you want to. Actually, no, that's actually a bad idea. I remember what I did here. So tangent of x turned into sine of x over cosine of x. And multiplying it by cosine squared, I just wrote that over 1. No issue there. And again, remember, cosine squared, that's really cosine of x times itself. And this allows me to cancel one of these cosines with this cosine right here. Okay? So once you do that, you have 2 sine of x cosine of x over this cosine of 2x. And looking at this, 2 sine of x cosine of x is sine of 2x. That's one of our formulas, one of our double angle formulas. So this whole thing is going to get replaced with sine of 2x. And notice that now that we have both sine and cosine represented as a double angle, 2x, this is really going to be tangent of 2x, because the sine over cosine. All right. And here in our last example, at least for these notes, we have tangent of x times 1 plus cosine of 2x. Go ahead and use, again, cosine of 2x equals 2 cosine squared of x minus 1. And once more, that's because this minus 1 and this positive 1, I can already see are going to cancel each other out, just kind of make things a little easier for us. So we can see, let me go back. We can see this cancellation right here. All we'll have left is 2 cosine squared x times tangent x. And from there, I turn the tangent x into sine x over cosine x. Also notice that I took the constant, or not the constant, but the coefficient too, and I moved it to the front. Okay, this is usually what I'm going to do. If I have a coefficient for a big piece like this, it's just all being multiplied together, I'm going to move that coefficient to the front. So move the 2 up front, tangent x, sine x over cosine x, cosine squared, I just put it over 1. And again, notice cosine squared, that's really cosine x times itself, where this cosine x will cancel with this cosine x, and all we have left is 2 sine x times cosine x, which is equal to sine of 2x by the double angle formula. And that's our answer. So every one of these problems here in today's video notes, they make use of a double angle formula somewhere. And a lot of them, as you can see, specifically like number 3 here, or here in example 5, you can be kind of clever about the double angle formula used in the case of cosine of 2x, a lot of times to help you kind of simplify things down a bit. All right.